Section 20.2 Ligand-Field Theory. Crystal field theory is very useful for us to make predictions. For example, we know dx squared minus y squared orbital and the dz squared orbital have higher energy than the other three d orbitals in an octahedral complex. However, in a tetrahedral complex, the dxy, dy-z, and dzx orbitals have higher energy than the dx squared minus y squared and dz squared orbitals. Well, this crystal field theory is useful, but it's also defective, because in crystal field theory, all ligands are modeled as point charges, and this is a overly simplified model. In ligand field theory, the ligand orbitals interact with the d orbitals, s orbitals, and p orbitals centered on the transition metal. And we can use ligand field theory to explain why bromidal is a weak field ligand, whereas cyanidal is a strong field ligand. Subsection A, sigma bonding. Now let's focus on the sigma bonds formed between the 6 ligands and the transition metal center in an octahedral complex. In an octahedral complex, we'll look at the atomic orbitals of the transition metal center, assign them symmetry labels, and then we'll look at the ligands. We'll do linear combinations of the 6 ligands, and it will assign symmetry labels to those linear combinations as well. So let's first look at the transition metal. Let's talk about a typical 3D transition metal element. We'll look at the valence orbitals. That means we will look at the 3D orbitals, 4s orbital and 4p orbitals. Let's look at the 4s orbital first. It's completely symmetrical, and then we assign A1G symmetry label to the 4s orbital. 4p orbitals, they have T1U symmetry label. So right here, T1U, X, Y, Z, T1U. If you look at the characteristic table for the octahedral point group, when you see X, Y, Z here, with this T1U symmetry label or irreducible representation, well, you know the PX, PY, PZ orbitals belong to this T1U symmetry species, and they are triply degenerate. And also, this X1Z, XYZ can be used to denote the translations in the XYZ directions, or the dipole moment in the XYZ directions. So again, when you see XYZ, they can be used to denote the translations in the XYZ directions. They can be used to denote the dipole moments in the XYZ directions, but in this case, they represent the PX, PY, and PZ orbitals. So right here, T1U. And then we have 3D orbitals, 5 of them. DX, DXY, DYZ, and DZX can be assigned this T2G symmetry label. So you can find XZ, YZ, XY here. The symmetry species is T2G. Alright, this is T2G, T2G here. What about the other 2 d orbitals, dz squared, dx squared minus y squared? Well, we can assign this EG symmetry label to this 2 d orbitals. So let's look for this x squared minus y squared. It's right here. This one looks a little weird, but this is the dz squared orbital. The wave function of 3d z squared is proportional to 2z squared minus x squared minus y squared. this is also 3z squared minus r squared. And that's why it's called 3dz squared orbital. Alright, because the concentration is on z squared. And also, you may view this as a combination, a linear combination of z squared minus x squared and z squared minus y squared. So again, this is proportional to the wave function of dz squared. Alright? So now we assigned the symmetry labels to the 4s orbital, 4p orbitals, and 3d orbitals centered on the transition metal. Now let's look at the ligands. Let's say we have 6 ligands. Each ligand has at least one lone pair that can be donated to the transition metal and form a sigma bond. So really, we are looking at the 6 sigma bonds. Well, you can also view this as linear combination of the 6 ligands, or in crystal field theory, the combination of 6 negative charges. But for now, let's just say 6 sigma bonds for simplicity. We can assign symmetry labels to the linear combinations of the 6 sigma bonds. Alright, we can't assign a symmetry to any one of those sigma bonds. For example, the ligand on top of the transition metal, we can't assign symmetry to that. We'll have to do a linear combination of the sigma bonds in a systematic manner. So first, we can just add up all those 6 sigma bonds with an equal weight on each bond. So it's just sigma 1 plus sigma 2 plus sigma 3 plus sigma 4 plus sigma 5 plus sigma 6. This is unnormalized, but still we can see the weight on each sigma bond is the same. And the signs are the same. Therefore, we say, well, this is totally symmetric with respect to all 48 symmetry operations in the octahedral point group. So this is the character table. This is for OH point group. And on top, you have 48 symmetry operations. Identity 8C3 symmetry operations, because you have 4 C3 symmetry elements, and for each C3 symmetry element, you have C31 and C32. C31, that means rotate by 120 degrees. C32 is rotation by 240 degrees. And then you have 6 C2 symmetry operations, 6 C4 symmetry operations, and etc. You have improper rotations, you have inversion, also improper rotations, etc. So again, we have a total of 48 symmetry operations, and also we say the order of this OH point group is 48. So when you do this linear combination, you will see this is completely symmetric with respect to all 48 symmetry operations. And then you can do this 3 linear combinations. In here, you have only sigma 1 and sigma 3. They are in the x direction, sigma 2, sigma 4 in y direction, sigma 5 and sigma 6 in the z direction. So this 3 have the same symmetry as the 4px, 4py, and 4pz orbitals. So that means this 3 will interact with the 4p orbitals of the transition metal. The symmetry label is T1U. U means angular order, and you can imagine the px, py, pz orbitals are antisymmetric with respect to the inversion center. And same here. Finally, there are 2 other linear combinations that belong to this EG symmetry species. This one corresponds to dx squared minus y squared Alright, so you have sigma 1, sigma 3 in the x direction, sigma 2, sigma 4 in the y direction. This is actually dz squared. And remember, dz squared is proportional to 2 times z squared minus x squared minus y squared. So over here, this corresponds to 2z squared. And then minus x squared. Sigma 1 and sigma 3 together corresponds to x squared. Sigma 4 and sigma 2 together corresponds to y squared. So over here, this corresponds to 2z squared minus x squared minus y squared. SALC stands for symmetry adapted linear combinations. And when you have 6 ligands, there are 6 sigma bonds. The 6 symmetry adapted linear combinations are A1G, T1U, and EG. Okay? Singly degenerate, triply degenerate, and doubly degenerate. Alright? And we can also look at the number of nodal surfaces in A1G, T1U, and EG. We have 0 nodal surface here, 1 nodal surface here, and 2 nodal surfaces here. And in general, the more the nodal surfaces, the higher the energy. So we can look at this energy diagram here. So these are the 6 symmetry adapted linear combinations of the 6 ligands, or you can say 6 sigma bonds. In here, I want to say those are 6 lone pairs from the 6 ligands. And you have A1G on the bottom with 0 nodal surface, T1U, triply degenerate with higher energy because they contain 1 nodal surface. EG contains 2 nodal surfaces. Alright, now let's look at the interaction between the lone pairs and the transition metal. So you have 6 ligands. Okay, so you can say this are 6 ligands or 6 lone pairs or 6 sigma bonds. And now if you look at the symmetry of this 6 ligands and the symmetry of this 4s orbital, they match. They are both A1G symmetry. Now let's look at the 4p orbitals. 1, 2, 3, 4p orbitals. Let's say this is px, py, and pz. And over here, this is actually sigma 5 minus sigma 6. Different signs. Over here, different signs, opposite faces. So these 2 match. These 2 also match. This is the py orbital, or 4py orbital, if we're talking about a 3D transition metal. Okay, 4p orbital. And over here, let's say this is 4py, and then these 2 are the 2 ligands in the y direction. Let's say this is 4px, 2 ligands in the x direction. So this 3 give you T1U symmetry. This 3 give you T1U symmetry. So this 3 match with this 3. So if you look at the ligands, and then you do the linear combinations, the A1G linear combination of the ligands will interact with the 4s orbital. Alright? And this 3 triply degenerate T1U linear combinations will interact with 4px, 4py, and 4pz. Okay? Let's say this is z direction, x direction, y direction. There are 2 more linear combinations with EG symmetry. This 2. So this one is sigma 1 plus, I think this is sigma 1 plus sigma 3 minus sigma 2 minus sigma 4. This symmetry match with dx squared minus y squared. This one is just 2 times sigma 5 plus 2 times sigma 6, and then minus sigma 1 minus sigma 3 minus sigma 2 minus sigma 4. So this is actually matching with the symmetry of dz squared. So this is dz squared, and this is, let me show you the equation here. The equation is here. This one will match with dz squared. Alright, so what does that mean? That means these two linear combinations will interact with dz squared and dx squared minus y squared. What about the other three d orbitals? We got dxy and dyz and dxz. These three are assigned T2G symmetry label. Alright, so these three are triply degenerate T2G. However, if you look at the linear combinations of the ligands, there's no T2G. That means the ligands will not interact with dxy, dyz, or dxz at all. So these three d orbitals have no interaction with the ligands in the octahedral complex. They will become non-bonding orbitals in the transition metal complex. So now let's look at the energy diagram. Over here, those are the 6 ligands. They form A1G, T1U, and EG linear combinations. And these combinations are symmetry adapted, and therefore we call this SALC, symmetry adapted linear combination of the ligands, or you can say of the 6 sigma bonds, or you can say of the 6 lone pairs. Now let's look at this 3D element. 3D, 4s, 4p. When the transition metal forms a complex, you may assume the 3D orbital lies below the 4s orbital, and 4s is below 4p. So even if you are looking at a scandium, supposedly if you're looking at a scandium atom, it's 4s2 and then 3d1. But when this scandium element, SC element, forms a transition metal complex, you may assume all 3 valence electrons occupy the 3D orbital. Alright? Titanium, you have 4 d electrons in a transition metal complex. Although we know that in a free titanium atom, it's supposed to be 4s2, 3d2. But again, in the transition metal complex, you move the 4s electrons to the 3d orbitals first. Alright, now let's just look at the interaction between those orbitals. Let's not put in any electrons in these orbitals yet. We learned this T2G orbitals, 3 of them, dxy, dyz, dxz, will not interact with the ligands at all. So we're going to have to draw this T2G here as non-bonding orbitals. There's no energy change at all. Non-bonding orbitals. And then you'll see this A1G interact with A1G. Okay? A1G interact with this A1G. So the lower orbital, lower energy orbital, now has even lower energy. The higher energy orbital now has even higher energy. And essentially, this A1G consists of mostly 4s orbital and a little bit from the ligand. This A1G consists of mostly the ligands and only a little bit 4s. So really, this one mostly is the 4s orbital of the transition metal. This A1G is mostly the totally symmetric linear combination of the ligands. T1U will interact with T1U. Alright? And this T1U has lower energy than this T1U. And this T1U mostly consists of the ligands. This T1U has higher energy than the 4p orbitals. And this T1U in the complex has is mostly 4p orbitals, 3 of them. All right, so you can just imagine this 4s and the 4p orbitals shift a little bit up there. All right, and then the A1G and T1U linear combinations of the ligands shift a bit downward here and here. Now it's really important to look at the EG linear combination of the ligands. It's going to interact with dz squared and dx squared minus y squared right here. Right? And this EG will go here. The lower energy EG will go down. The higher energy EG will go up. So really this EG has higher energy than dz squared and dx squared minus y squared. And this two doubly degenerate EG orbitals in the complex are mostly 3dz squared and 3dx squared minus y squared. It consists of a little bit contribution from the ligands. So this EG in the complex consists of mostly the dz squared and dx squared minus y squared, and a little bit ligands. So in that sense, you can still view this 2EG as the dz squared and dx squared minus y squared orbitals. These three are just dxy, dyz, and dxz. Now you can see this T2G orbitals, dxy, dyz, and dxz, do not interact with the ligands, therefore they are non-bonding orbitals. There's no energy shift. The other two 3D orbitals now become antibonding orbitals. They shift up, and that creates a gap right here. And this energy gap is delta O. You learned delta O in crystal field theory. Now you see the same delta O in ligand field theory. In ligand field theory, delta O originates from this two 3D orbitals becoming anti-bonding orbitals. Alright, that's the origin of this splitting in ligand field theory. And now let's look at the tinted box again. The T2G orbitals are non-bonding dxy, dyz, dzx. Okay, right here. The EG orbitals are antibonding orbitals, mostly consist of dz squared and dx squared minus y squared. Alright? The difference is delta O. And this prediction matches with the prediction in crystal field theory. And then let's look at the bottom 6 bonding orbitals. 1, 2, 3, 4, 5, 6. This 6. Okay, mostly consists of the lone pair electrons from the ligands. Alright, so there's energy shift downward. Okay, so those are bonding electrons. And this is non-bonding electrons. Okay, and over here, anti-bonding electrons. Okay, anti-bonding orbitals. Okay, there's two this one and this 3 are anti-bonding orbitals. Now, the stronger the interaction between the ligands and the metal, the more strongly the anti-bonding of the EG orbitals. Why is that? In molecular orbital theory, when two interacting orbitals have similar energy, the interaction is going to be stronger. And the lower energy orbital will be shifted much lower. The slightly higher energy orbital will be shifted much higher. Okay. when two orbitals have quite different energies, they tend not to interact with each other. And even if they do, the energy shift is minimal. So in this sense, when the 3D orbitals, in particular the two EG orbitals, have similar energy as these two EG orbitals, we will observe stronger interaction, and this 2 EG will be shifted down significantly, and this 2 EG will be shifted up significantly. And then you'll have larger delta O. And also, when the two orbitals are far away from each other in space, the interaction will be minimal. When they are close to each other, when the overlap is significant, and then you will see significant shift, energy shift. So that tells us when we have a 4D or 5D transition metal center, because the 4D and 5D orbitals are more diffuse than the 3D orbitals, there's going to be a more significant overlap between the 4D, 5D orbitals and the ligands. And then you'll see larger delta O. Alright, so when you have 3D, you'll have a smaller delta O. 4D and 5D, you see a larger delta O. And then we can look at the high spin versus low spin electronic states. We learned that this is going to be determined by comparing delta O and P. P is the electron pairing energy. This is because if you put two electrons in the same d orbital, there's going to be stronger electron repulsion. So if delta O is less than P, that means we have weak field ligands, or 3D transition metal, or both. We have a small delta O. When delta O is smaller than P, high spin is favored energetically, because we're trying to minimize the number of paired electrons. When delta O is greater than P, so for example 4D or 5D transition metal, or we have strong field ligands, and then delta O is greater than P. In this case, we'll try to put electrons in the lower energy orbitals, and then low spin is favored energetically.